previous class, we were discussing about the dynamic characteristics of sensors, right? So we saw dynamic characters, something which is steady when the system is under motion. In our case, the system here is sensor system, right? So since we are talking about dynamic characteristics, we are considering time, right? So this is a small example. This actually is not a single video, but it is like some 32 images that is run fast over time, right? So when you do it, pictures will look like that is a video, right? So that is how static and dynamic objects differ, right? Static object, when it is moved over time, it will become a dynamic object. This is a best example, right? Then there are different dynamic characteristics. Here what we are going to see is dynamic response. Under that we have speed of response, lag, fidelity, and dynamic error, right? So this all we have seen in previous slides itself, I mean in our previous session itself. However, speed of response, it is the rapidity with which the measuring system responds to the measured quantity, right? Let's say we are using a what do you say, bike speedometer, right? We all use bikes, right? So in the bike speedometer, if you see, the speed of the bike, or the speed at which the engine rotates, should be, the RPM should be uh, like it should be displayed at that instant, right? We don't need the already completed value. We need the value at that instant, right? So we need a system with good speed of response, right? I hope you can understand this. The speed of response is the rapidity with which the measuring system responds to the measured quantity. Best example would be of speedometer. And then measuring lag, it is the it is the delay or retardation in the measuring system in response to the measured quantity. The best example I told you was sphygmomanometer, right? Under this measuring lag, we have two types. One is retardation, the other one is time delay. Retardation is like measuring the system after the measured quantity is being changed, right? Sphygmomanometer again will be the best example for that. Then time delay is measuring the system which responds after dead time. We are about to measure something, but the measurer, it actually has zero value for a few seconds, and then only it will start recording or still showing output, right? So this dead time, when considered under the study, then we can call it as a delay, a lag, which comes under the category time delay, right? So two categories, retardation and time delay. The next is fidelity. Fidelity, again, we saw in our previous session. Again, it's a small brush up. It is a degree of closeness in the measured value and the measuring quantity, right? Just example for this, wireless fidelity Wi-Fi, right? Wireless, Wi-Fi is supposed to have the best range, not range, best transmission of data. The reason, that is why it has been named as fidelity, wireless fidelity, the closeness between the measured quantity and the system that is transmitting. And then loading effect, right? So loading effect is what we are going to see. So loading effect, the statement here says that it is the change in the measured quantity due to the influence of the measuring element, right? So let's say you're working in biochemistry laboratory. You have worked in biochemistry laboratory. You have measured pH, right? You have measured pH. So while measuring pH, if you see, you'll be having a solution in a test tube, right? Use that, right? Then in that solution, you'll be inserting a electrode, right? So when you insert the electrode, what happens? The ions move between the solution in the test tube and the electrolyte. As a result, there will be a small production of current, and that current will be measured. Based on that current or the voltage, we will be telling the value of pH, right? But while inserting the electrode, what happens is that, and the electrode is a metal, right? So due to this metallic nature, what will happen is when inserting, this metal will disturb the ions, right? As a result of the metal used, what will happen is the solution that we are about to measure will get disturbed, right? This effect is called as loading effect, right? So that is what has been saying. The measured quantity will change because of the influence of the measuring element. The measured quantity here is the solution, right? The solution's value only we have to find out, but the electrode while placing will change the value of the measuring quantity. So right, this is what we call it as loading effect, right? Anyway, in future while doing experiments, we will see about this loading effect much more in detail, right? The next is, okay, impedance matching. This is very important topic which you have already studied in few of your electronic classes. Impedance matching. Impedance, what is it? Is resistance actually, but as you said, as most of you said, it is a kind of an effective resistance, but it is found only on AC circuit. Okay, while dealing with DC circuit, the resistance will, the resistor will only have resistance, whereas while dealing with an AC circuit, most of the resistance will be considered as impedance, right? Not only that, if you see a capacitor, if you take a capacitor, the capacitor, you know how a capacitor is being built, right? Two parallel plates. This parallel plates, when an electricity comes to this parallel plate, what will happen is that there will be small resistance present in that capacitor also. That also we can call as impedance, right? So impedance presence in impedance is a resistance actually, as you most of you said, impedance is resistance, but as you, like most of you said, it is a resistance, but it is during, due to the influence of AC power supply, right? So that is the main difference. So keep that in mind. Impedance is something, or it's the same as the resistance, but it presents only in the AC circuit, right? So that is why in only while using AC circuit you can come across this word impedance, right? The impedance is not resisted only, not restricted only to the resistor. It is also present in inductor, capacitance, and every other circuits. Okay, right. So now impedance matching, again you have studied impedance matching and maximum power transform theory. All those are kind of interrelated. So what is being said in this slide is that maximum power is transferred, and then the load resistance equals to the source resistance. Okay, this is what is called as maximum power transfer theory. Okay, maximum power transfer theory. Yeah, okay. Sorry for that. Uh, right. So maximum power transfer theory is what we just discussed. Okay, so it is like when the maximum power has been transferred, right? So for that, in our circuit, the load resistance must be equal to the source resistance, right? That is what is impedance matching. Best example in this case would be, let's consider the small animation. Okay, you know there's a power supply that is being given. In this case, I'm not given a AC supply. Let's consider, okay, a rough idea. So here initially the RS is the source resistance, RL is the load resistance. Load resistance in here we are using a speaker. So if you see, while giving supply, the source resistance is initially low, right? And that at that time, if you see the you're now seeing the yellow color lines, which means the volume is little low. Then what happens is the load resistance then becomes higher than source resistance. In that case also, if you see the red color lines, again it is the volume is low. But when the source resistance equals the load resistance, then what happens is the volume becomes very high, right? This is the point where maximum power is transformed. That is why we name this particular theorem as maximum power transform theorem, right? Maximum power is being transferred, but you also have to keep in mind that during maximum power transform, the efficiency is reduced. Okay, only the power is maximum, but the efficiency of the system will be low, right? So we'll move to the next one. This is overshoot. Okay, so you can read from the slide. Overshoot is like when the input is given to the system, the move it points, like the pointers that you see in your voltmeter or ammeter, what will happen is it will move to a point beyond the original value, and then it will come to the normal state. If you see in your electronic circuits lab, you have used ammeters, voltmeters, right? So if you haven't seen this, next time when you get into your lab, connect a voltmeter to the regulated power supply RPS that you have already used. Connect it and keep 5 volts supply in your RPS and turn on the circuit, if you see, the voltmeter pointer will move beyond 5 volts, and then it will come back to 5 and be steady on the value showing 5 volts, right? That is because of overshoot, right? So whenever we pick up a system, we should make sure this overshoot is low, right? So these are all the dynamic characteristics, right? So this is a small example of what I just told, right? I'm here, I'm giving 1.5 volt. So if you see, I'm connecting a switch here. So if I close the switch, if you see, instead of showing 1.5 in the initial minute, what will do is it will go beyond 1.5, it goes up to 3 even, and then comes back to 1.5, right? So this is called as overshoot, right? Okay, so we'll have a small brush up on what we saw so far. So dynamic response involves speed of response, then lag, fidelity, dynamic error, right? So dynamic error we'll be seeing in the next part. So speed of response is the rapidity with which the system responds to the quantity. Measuring lag is the lag between the system that is being measured and the measurement we get. The best example is sphygmomanometer, right? And this is two types. One is retardation, the other one is time delay. Retardation is best example is sphygmomanometer. You can remember sphygmomanometer. Time delay is when the dead time is also considered, right? Then fidelity, keep in your mind Wi-Fi, right? You don't have to think of anything else but simply Wi-Fi. Then loading effect, remember the pH that we used to measure, right? Then impedance, maximum power transfer, you can remember using this loudspeaker example, right? The loudspeaker will be at full volume. Remember, it will be at full volume when the load resistance is equal to source resistance, right? It can also be called in AC circuit when the load impedance is equal to the source impedance, right? So that is why here in this part we have given it as impedance matching. We are matching the impedance, that is the load impedance is being matched with the source impedance, right? So while doing that, we will have maximum power, but we have to be very careful that the power alone is at max, but the efficiency will not be at max, it will be considerably low, right? In most of the cases it will be around 50%, right? Then overshoot. The best example is what happens when your voltmeter display shows when you turn on the RPS, right? In the first few seconds, like in the first millisecond, if you see, it will go beyond 5 volts and then come back to 5 volts if 5 volts power supply is key, right? In this case, I've given 1.5 volt, it goes beyond 1.5 volt and then comes back and be steady at this particular point, right? So this is what is called overshoot, right? So next, we are going to see about errors, right? We all know what errors are, right? Errors are quite common. Errors are quite common. We know. We can simply say, since we are dealing with measurement, I can say, we can simply say that the difference between the true value and the measured value is error, right? That is what we saw in our very first class, right? The difference between the true value and the measured value, that is what is called error. So under this error, we have few types, like we have random error, we have gross error, and we have systematic error, right? So if you are quite good with English vocabulary, you would have understood what this really means. Okay, random error, as the name indicates, is something random. Gross, again, it is a compilation of certain characters which will be staying in the coming slides. Systematic error is something related to the system itself. System here the measuring system or the instrument, right? So gross error is the error that arises due to the mistake of the experimenter. In case, let's say, when we are in our laboratory, when we are asked to do few experiments. For example, let's take you're in a electronic circuits lab. Okay, you are asked to study the characteristics of a diode. Okay, while studying the characteristics of a diode, what you do is you keep the circuit, you connect the connections as per the circuit diagram you have drawn previously, and while taking the measurement, if you connect the experiment, the connection properly, there will not, the output will be proper. But there are cases, what could happen is that you could have misplaced, or you could have wrongly placed the diode. Like you can inverse the light, you could have connected the inverse connection, like the in place of anode you could have connected cathode. In that case, the output will not be proper, but you will be marking that output saying the system is not proper. But the reason is the mistake of the experiment. You have not connected the diode in proper polarity if the terminal is not connected properly. Or there are cases where you will not connect the ground and power supply properly. There are also cases where the ground and power supply wires, the metal contact is not proper. So all those mistakes are the mistakes caused by the experimenter himself. So those experimental errors are called as gross error, something that we do, right? We in sense the experimenters do, right? The next one is systematic error. Systematic error is something related to the system. So here we have classified the systematic errors into three types. One is instrumental, then environmental, and observation, right? So again, self-explanatory words. Instrumental, something purely related to instrument. Environmental, because of the environmental factors such as temperature, humidity, all this. Observation, the way we observe. Again, this observation error can also be sometimes related, can also be called as gross error, because observation is being made by the experimenter himself, right? So I will give a classical example, but before that, instrumental errors, if you take, there are again three main reasons why this instrumental error takes place. First reason is the inherent shortcomings in the instrument. I'll tell what that in the next slide. Then second reason is misuse of the instrument, and the third reason is loading effect of the instrument. Remember the loading effect that we discussed a few minutes ago. That's the so inherent shortcomings. If you see, the reason is mechanical structure. See, we need certain type of sensor to be in the form of certain shape. But if you replace it, like if we need a square shape sensor, and if we are using only a circular shape sensor, then we will not get the output properly. One best example is, let's say, since we are all biomedical engineers, we know what EEG, ECG, and all those things, right? ECG, for example, let's take, in this case, let's take ECG electrode. ECG is electrocardiogram. Cardio is something related to heart. Gram is some kind of a measurement, a meter, right? So what we are going to do is, we are going to measure the electrical activity of heart muscle. So while measuring it, we need a specific type of electrode, right? So that electrode, in most of the cases, we will be using a adhesive type. Adhesive type, like in sense, the electrode can stick to the parts of your body, right? In that case, if instead of using that kind of electrode, if you use a normal electrode or a simple metal wire, the output will not be proper. That is what is called as inherent shortcoming of the instrument, right? A simple metal wire cannot properly use. Properly cannot, a simple wire cannot get the output easy. We need some precautions, right? So that is the mechanical structure. And how can we correct it? By properly planning on the measurement. Let's say, suppose we don't have the adhesive type of electrode. In that case, we'll have to properly plan on the measurement. Like if we have only metal wire, then we have to properly take care. Like, see, we need adhesive electrode because that adhesive electrode will be stable on that position, and it will also have an inbuilt gel system, so that the intermediate hair will not be a problem. It will not create error. Whereas if you don't have that, we'll have to properly plan for the wire that we have, right, in our hands, right? So how can we do that? First will be removing hair, then using proper gel, right? So that is the error correction strategy. That is the first point, which is proper planning on measure. And second one is calibration. Since we are not using like, what do you say, a predefined sensor or electrode, we are only using something else. So that something else should be calibrated properly with the golden standards, right? Then the last one is correction factors. Suppose the electrode or the metal wire that you have can only measure a certain value, then you have to apply the correction factor and make sure your reading is being correctly given, right? Then next one is misuse of equipment. This is very, very important. Misuse of equipment. This is what most of us do in our laboratories, right? The instrument can work under certain conditions, but if you misuse it, the instrument will not work properly. Best example is, yeah, let's say a voltmeter. A voltmeter, if you take in the reading section, you can see the voltmeter can, there are different types of voltmeter. Let's take, there is a voltmeter with a range of 0 to 5. If you give 10-volt power supply to the voltmeter, what will happen? The voltmeter will obviously run out, right? It will wear out, right? It will get broken. It cannot withstand more than 5 volt after a particular time, right? That is misuse of instrument. Right? The instrument is supposed to be used at a particular condition, but if you deny it or if you refuse to use at that particular condition, then we can state that that as misuse of instrument, and that will completely damage the instrument. Right? So the cause, as I said, is not using the instrument properly. Error correction is properly handling it. If the voltmeter can measure only 0 to 5 volt, then use only 0 to 5 volt power supply. Right? The next one is loading effect. Okay, so loading effect, we actually saw what loading effect is, right? So error correction in this case would be planning the system that can nullify the loading effect, right? The next environmental factors, the surrounding factor like wind, the temperature, dust in the system, so all that could influence, right? So let's say we are measuring the temperature, right? If you measure the temperature of a human body in a normal condition, it is fine. But if you measure the temperature of a human body, when he is exposed to sun, what will happen? The temperature will obviously be high. If he is in a sitting in an AC room, then obviously his temperature will be low, right? So this all should be considered. This could also cause error, right? Similarly, while measuring the center of gravity, while playing with the pendulum to measure the center of gravity, if there is more wind, what will happen? The wind will influence the pendulum, right? So that time we will not get the correct output. Right. Similarly, in your biomaterials laboratory, in biochemical laboratory, if you see, you will be taking small amount of chemicals, right? You'll be taking that in a paper and you will be putting in weighing balance. Remember, you have done that in your biochemistry lab. While doing that, if there is a dust, what will happen? It will show extra white, and then the complete output will be ruined. Right? That is again is a error. Right? So all these factors will be considered. Now, how can we correct it? First one is we have to make sure the condition is constant. If the experiment should be done under a certain room temperature, that is what should be done. Then immune equipment in sense, certain equipment cannot be used uh, in the places which is exposed to sunlight. You should not do that. Right? Similarly, certain equipment cannot be exposed to water. So that should be done, or you have to buy an immune equipment. If you see, most of the equipment that we see in our laboratory, the ECG machine, EEG machine, that are all made immune to the external environment in military cases. Right? The military, the ECG machine is being used in military, but there they will use materials that are immune to all those conditions. Right? So that is what we are also asked to do. Use immune equipment. Then use techniques to eliminate them. Right? We have the different type of environment. So the one best example for this would be the laminar airflow chamber. In your biochemistry lab, again, you have seen a laminar airflow chamber, right? A small chamber in which you will be using candle and you will be doing different experiment, right? So that is a technique to eliminate bacteria or virus contaminating or going outside and contaminating the environment, right? The next one is computer correction. You can use computer correction. If you know that there are certain environmental factors that we cannot correct it, then we can use computer correction, which will get us the correct value. Right? The next type of error in systematic. See, first we saw what is instrumental error, then we saw what is environmental. We just saw what is environmental. The last one is observational error. Right? So observational error is like again we'll go back to our EC lab. Consider you are sitting in your EC lab and you're asked to do or find the characteristics of a diode. Right? While measuring it, you'll be standing on the right side of the voltmeter. Let's say you're taking value from a voltmeter. You're standing on the right side of your voltmeter and your friend is standing on the left side of your voltmeter. If you see from the right side, you will be seeing a value. But if you see from the left side, your friend could see a different value. Maybe it could vary only by a small point, but still the value will differ. So what we have to do is we have to stand straight to the machine to measure the instrument. Another simple example is like you and your friend are sitting opposite to each other. Right? If your right sits, your friend opposite will read it as 9. Right? That is observational error. The same thing could happen in the instrument also. Right? So that is observational error. And the last one is random error. So we saw different types of errors so far, right? So the things or the errors or the noise that were not involved in the above set category will come under random errors.